So just to recap what we did in the first lecture, we kind of motivated the scene by talking about time-ordered data. So this is the kind of data that we're interested in studying, and we formalized it in the concept of a path. So then we introduced this feature of paths called the signature, and began looking at some of its properties. So the first one was these ODEs. So we showed that the signature can determine special linear ODEs. And then we discussed some of the kind of the elementary geometric properties of the signature. So we saw, for example, that it was invariant under reparameterization. So really the signature is a function on unparameterized paths. So then at the very end, we came to some more algebraic properties. So we started off with this with the shuffle product. So last time I sort of motivated the shuffle product as saying that with the question of why is the signature like a polynomial. So I gave this definition of shuffles. I kind of defined what the shuffle product was for two different words. And the simplest way to understand it is just to look at an example, like the one on the bottom. Okay, so now hopefully things are actually working. Okay, good. So this was the theorem that I presented right at the very end, after an unconscious question as to why the shuffle product is what it is. So the reason that we introduced the shuffle product is because it yields a very elegant identity for the product of two signature terms. So the content of the theorem is, let's look at a path X over AB into RD, and two words I and J. And then the content of the shuffle product identity is that we can express the product of these signatures as a sum over signature terms of higher order. And the order of the signature terms is that of I plus J. So note here that the length, of the word is equal to the length of I plus the length of J. This is for all K. So this is kind of like a polynomial type property for signatures. And I'll emphasize this a little bit more. So again, as a concrete example, think of a path taking values in R3, so in any path that you like. And then the product of the two signature terms 1, 2 and 2, 3 is given by the sum of the following terms. So when you shuffle all the indices according to the rules that I described before. So you'll notice that some terms appear more than once. So for example, this term here, and this term here, they both appear, they appear twice. Okay. So this is quite a classical result, although when it was discovered, it illustrated quite a nice property of iterated integrals back in the 50s and motivated their further study. Okay, so I've included a proof of this, which I'll go over briefly. So with the other proofs that we've seen, we're going to use induction. So I'm going to just write out the first line is essentially just the definition of the two iterated integrals. And then in the second line, we're going to use Fubini. So this is a product of two integrals. So I can write it out as one big integral over the product space. So here the integration variable is S and T over the product of the integral AB with itself. And again, this notation is really just, it's nothing but x dot sik times x dot jm t ds dt. So it's just every time you see a dx, just formally replace it by its time derivative times dt. Okay, so far it's quite okay. And now what we do is so the trick is now we consider two cases. So we know that either s is going to be less than t or t is going to be less than s. inside of this integral. So we're going to separate out those two cases. And in each case, if s is less than t, then notice that we can combine this this term with this integral term dx iks in order to obtain and integrate over s in order to obtain the signature of just the word I. So this is how this integral corresponds to the regime s is smaller than t. And I'm going to leave t as it is. And then this part here, this corresponds to t being less than s. In which case I do the opposite. So this in green. Here I basically just combine these two guys together and integrate up in t. And I don't integrate in s. All right, I leave the integral in s as it's written. Okay. So, once we've done that, we're going to apply an induction. So we're going to assume that we've proven the claim for all words whose combination, whose combined length is smaller than, say, so if the word is of length, if we're looking at the word I and j of length k and m, then we're going to assume that we've proven the claim for all words of length k plus m minus 1. So here, this is such a word. So basically, we're looking now at I and the word this is j, but we've lost the last letter. So we can apply the inductive hypothesis to this product here and obtain that replace this product by this big sum over here. This is the inductive step. And we're going to do the same thing over here. So we're going to replace this guy by this sum. Okay, so this is where kind of the recursive nature of the signature plays quite an important role. And then from here we can actually already conclude. And what we do to conclude is we use kind of a combinatorial identity. So so the shuffle between two words I and j can also be defined. I define it as kind of like intertwining all of I and j together, but while preserving their order. But it can actually it has an equivalent inductive definition. So the shuffle between I and j can be defined as sort of the multisets given by combining all the words in the first multiset here and the second multiset here. And in the first multiset, what we do is we take all the shuffles that appeared between I and the word j where we lost the last letter, and we just append j to the end, and vice versa for the second multiset, but where we replace the role of I and j. So this is essentially this combinatorial identity essentially follows from the fact that whenever we shuffle two words together, the last letter of the resulting word. So I don't know where exactly you lost me, but I'll just say that. So this combinatorial identity with the shuffles is kind of interacts very nicely with this domain of integration for the signatures. Okay, so this is a proof of the shuffle identity. Okay, so just to quickly summarize the impact of this of kind of what this entails. So as I said before, signatures really behave like, in fact, they generalized polynomials. So if you applied this shuffle identity to piecewise linear path, to a linear path that goes from 0 to x, so we saw that this encoded all the polynomials of x, then you'll essentially just recover the fact that product of two polynomials is a polynomial. Kind of it generalizes to in some sense a non-commutative setting polynomials. So a particular consequence of this is that if we let, for example, denote by A the set of functions on paths, so the set of all functions from paths to R, which are of this form. So we look at sums of, sorry, and then my cast stops working as well. 1 second. Okay. Okay, we're back. So if we denote by this mathcal A, the set of all functions from paths into R, which are of this form. So I'm going to take a sum over all of my words and just stick some coefficient in front of the signature term associated to the ith letter. Okay, to make this well defined, I'm going to assume that all by finite remaining of the C is 0. So I'm going to look at this space of functions. So this is a vector space of functions. Then what the shuffle product tells us is that this the space of functions actually is an algebra of functions. So it's closed under multiplication. If we think about the Stone-Weierstrass theorem, what this tells us that signatures should well approximate continuous functions. So this is quite a powerful theoretical as well as practical tool. So in practice, it sort of justifies the use of signatures, just like polynomials are good features. So this it means that the signature should be a set of good features. And for theoretical purposes, it means that we can prove quite nice properties about the signature. So as a small aside, one of these nice properties is a solution to the so-called moment problem, now for signatures. So recall that on Euclidean space on RD, moments can determine probability measures. So if we look at two probability measures P and Q, then if we look at all of the polynomials associated with these probability measures, and it happens to be that they're equal for these two for P and Q for all words, then this is equivalent to P being equal to Q. So this is and again under some integrability assumptions. So it's actually, this is not true in general, but you can find counterexamples. But all the counterexamples have moments that grow sufficiently quickly. So if you bound the growth of moments, then this equivalence holds. Okay, so this followed from the Stone-Weierstrass theorem, or more generally from Karlmann's condition. Okay, so it turns out that so perhaps not so surprisingly, in view of this shuffle product identity, you can actually prove a similar statement for probability measures on paths using signatures. So suppose that P and Q are probability measures on paths indexed by AB. Then essentially a very similar statement holds true as it did for vectors. So if this collection of sorry, I don't need the brackets here. So if the signature associated to the ith word under the probability measure P is equal to the signature associated to the ith word under the probability measure Q, for all words, for all words I, then this is equivalent to P being equal to Q. And this is again modulo integrability assumptions, because this is necessary even for Euclidean space. And it's also modulo tree-like equivalence. So remember that the signature wasn't able to pick up, tell the difference between any two arbitrary paths. But if you kind of mod out that equivalence relation, then you kind of you get a mathematically correct statement. So this was actually a problem that I looked at in my thesis that I did with Terry Lyons. Yeah, so kind of let me just say very briefly that the proof of this actually goes through a Fourier transform on path space. So one actually first introduces a Fourier transform and then shows that these kind of moments, these expectations of the signature, determine this Fourier transform. But the Fourier transform always, just like the classical Fourier transform, it always determines probability measures without any integrability assumptions. So what I want to say by this is that this kind of further gives motivation that the terms of the signature are like polynomials of the path. And now this is even in a probabilistic setting. So it tells you that it suggests that these expectations of the signature, they're the natural analog of moments of probability. Okay, so now it pass. And so, of course, I phrased this all in terms of the bounded variation setting that I was talking about. But this all applies in kind of a natural rough setting. So, for example, this would apply to Brownian motion. So Brownian motion satisfies these integrability assumptions that one requires. So the expected signature of the Brownian motion uniquely determines like trajectories of the it uniquely determines the random signature of a Brownian motion. Brownian motion up to tree-like equivalence. Okay, so having, I think I've spoken now probably enough about the shuffle product. So let me move on to the second important algebraic quantity or property. So the second property is called Chen's identity, and it's motivated by the question, at least for us, it's motivated by the question of how to compute the signature efficiently. So this is now heading more into kind of the realm of applications. So if one was actually to write a package or a library of how to compute the signature, this would be a very relevant question. Okay, so there's a first option, which is just to use the definition of the signature. So you just the definition of the signature is given by integrals. So you just take your quadrature method or something, and then you evaluate the integrals. If you're lucky, maybe you know that your curve or your path is given by polynomials in time. In this case, you can explicitly solve it, and this gives you quite a rapid way of computing the signature. This is very effective for polynomials, but it's less effective for something quite simple like piecewise linear paths. So if your path kind of has maybe 10 line segments, then taking that integral directly is going to be actually quite painful. So one might like to look for another method. Okay, and this is what Chen's identity allows us to do. Okay, so try this. So okay, there's a couple of instances here. Okay, so let me write it out. Okay, checked before that it was all right, but clearly not. Okay, so the theorem of Chen is the following. So this is Chen's identity. I'm going to present it actually in several different ways. The first way I'm going to present it is in terms of coordinates. So Chen's identity states that for x in the space of paths from A to C into RD and A less than B less than C, and any word I1, IK, the space of words, it holds that the signature over x of I1 IK over the full integral AC can be written in terms of the signature over the integral AB and BC in the following way. So we take the sum over all m from 0 to k, and we look at all the subwords. I1 until IM of AB times the signature of over BC of the sum over IM plus 1 dot IK. Okay, so what Chen's identity allows us to do is it tells us that if we know the signature of a path over sort of an interval AB, and a neighboring interval BC, then we can compute the full signature over AC according to this formula. So we just need to take a sum over certain multi-indices and products. Okay, so I'm going to show how to do this in practice. So consider a piecewise linear path. So let x go from the interval 0 to 2 to R2, and that's linear on the time interval 0, 1 and the time interval 1, 2. And it starts off at the point 3, 3, 0, goes up to 3, 1, and then it moves along to 0, 1, like this. Okay, so then so we would like to compute the signature first over the time interval 0, 1. So this we already saw how to do. Over the time interval 0, 1, this is just a straight line. So we saw that this was given by essentially the polynomials of the increment. So if we work it out, the time interval, the signature over the time interval 0, 1 is the only non-zero terms are given by the words, well, by the empty word, by the word 2, and by the word 2, 2, because the increment is only in the direction x2, so only in the y direction, and it's 0 otherwise. And for the increment over the time interval 1, 2, which happens only in the x direction, a very similar thing holds. But now the only non-zero entries are the empty word 1 and 1, 1. And now here we get that because the displacement in the x direction is now -3. So this is where this -3 comes from, and then we get that object squared divided by 2, and then it's 0 otherwise. So this was very simple to work out from the formula that we sourced from the very first exercise that I gave in the first lecture. Okay, so this is an application of that exercise. And then what Chen's identity, so I'm going to first work out a very baby step in Chen's identity. So I'm just going to work it out for the first level of the full signature, just to show you how it's done. So what Chen's identity tells us is that we need to break up the word. So when we look at the word, just the word 1, we need to break it up into all subwords. There's two ways of doing this: either the empty set followed by 1, or the empty set, or the 1 followed by the empty set. So if I go back to the statement of Chen's identity, this would correspond to, so here k would be equal to 1, and m would be either 0 or 1. And if m is 0, then this, so let me write about it explicitly. This is equal to 1 if m is 0, because this would be kind of the signature term associated to the empty word. And likewise here, this term would be equal to 1 if m is equal to k, because this would again be the signature associated to the empty word. Okay, so if we use that rule, then we see that there's essentially, Chen's identity tells us that there's two terms in here. So the first term for the signature associated to the word 1, it's going to be the sum of the corresponding signature for the same word over 0, 1 and 1, 2, and likewise for the word 2. And so what we get in total is that we get -3 plus and 1. And this is completely expected because we already saw that the first level of the signature was just the increment of the path. Of course, if I subdivide my path into 2 parts, then the total increment is the sum of the two increments of this over the subintervals. This is nothing surprising. This was just an example of how to kind of more definition chasing than anything. Okay. Something a little bit less trivial is to look at the second level. So let's work out the signature of the word 1, 2 for this path. So then, just as before, we have now we have three possibilities for that index m over which we sum. So either m is 0, in which case we get the first term, either or m is 1, in which case we get the second term, or m is 3, in which case we get this we get this third term. So notice that kind of the this 1, 2 here, it has to be the same always, and so you kind of break it up over all of the over the intervals 0, 1, and 1, 2 in all possible ways, while preserving the order. So I hope the kind of how this computation is done is clear. Okay, and then we just, we know what the signature over 0, 1, and 1, 2 is, so we just substitute all of those numbers in. So if we do that for the first line, we just get 0 as the final answer. Then if we perform the same computation, but for the word 2, 1, then we just swap around the orders of 1 and 2. And if we compute, if we insert the values of the signature for this new word, we get -3 as the final answer. So this gives you a way of computing. So now we've essentially completely computed the second level of the signature, because 1, 1 and 2, 2 we already knew. Okay, and so this, I'm not sure that there is a simple way to do this using kind of integration directly to see that this would be the correct answer. But Chen's identity ensures that this is the case. Also, just as a remark, notice that this is consistent with this geometric notion of Levy's area that we saw before as well. So if we looked at this path and we connected up the end with the beginning, according to this, according to a straight line like this, then this is this gives us a loop, and the loop encapsulates this area here in the counterclockwise direction, and so I think I must have confused when I was presenting Levy's formula. I think I confused counterclockwise with clockwise. So this is counterclockwise, which should give you a positive signed area. I think back then I said it was negative, but I think that was incorrect. So this is now counterclockwise, so it's the positive signed area, and so we notice that this is exactly going to be s of x 1, 2 minus s of x 2, 1. This is equal to 3, because so if I just subtract -3 from 0, and then this is exactly 2 times this area, so which is equal to 1.5. So you can see that this is a triangle with base length 3 and height 1, so its area is 1.5. So this is completely consistent with Levy's with the interpretation as Levy's area, provided that you get the counterclockwise and clockwise correct, which I did not at the beginning. Okay. So having presented this example, I want to go over again the proof of Chen's identity. So as before, we're just going to start off with the definition of the signature, and we're going to straight away break up the time integration from A to C into two parts, so A to B and C to B. So we're going to write out this signature as a sum of 2 integrals. So the integrands are identical, not just only broken up the integral. I'm going to apply induction here. So then I'm going to, so here, this is just the definition of the signature over the time interval AB. So I haven't done anything here. But for the second guy, I'm going to apply induction. And I'm going to replace this guy here, because T here is a parameter that goes from B to C. So I can apply kind of Chen's identity with C replaced by T. And this gives me this expression here. So I assume that Chen's identity holds for all words of length k minus 1. And I'm using this inductive hypothesis here. Okay. And then I noticed that this term here, it doesn't depend on T anymore. So I can pull out this term outside of the integral. This term becomes this term here. And then I can apply just the definition of the signature again over the interval B to A. Over the interval B to C. And so, so this integral combined, with this guy here gives me this final term. Now I notice that I have a sum from m to up until k minus 1. And then I have kind of this final term here is essentially like it corresponds to precisely the terms that appear in the sum, but with m is equal to k. And so all I do is then I just I pull it into the sum and decrease the index of the sum. Okay, so this is a very simple, again, inductive proof of Chem's identity. So I want to present these proofs because I think they kind of demystify some of the properties of the signature, and they show you how to think about it as a recursive object. Okay, so I'm going to now present Chen's identity as well as the shuffle product identity in a slightly different way, which is perhaps a little bit more appealing mathematically. So before I've just given it in terms of sums of special objects. Now I'm going to give it in a slightly more compact formula, which is which I think reveals a lot of structure and how the signature looks like. So for this, I need a little bit of notation. So I'm going to denote by this double bracket, this T double bracket RD, as the vector space of all formal series. And these formal series are in D non-commuting indeterminants, which I'm going to call E1 up until ED. Okay, so just think of these guys as some generators of an algebra, and they fully don't commute. So E1 times E2 is not equal to E2 times E1. Sometimes this is called the space of tensor series. Okay, so a generic element of this series looks like this big sum, and these coefficients Ci1 up until Ik. They're not going to be finite. They're not going to be kind of non-zero only for finitely many guys. They're going to be. They can generically be non-zero for all words I. So this is there's no question about convergence here. This is just a formal series. So this is not an analytic object. It's a purely algebraic object. So then notice that essentially an equivalent way of thinking about this this vector space of formal series is functions from words into R. So for every word I, I'm going to give you a number, and this number is going to be this coefficient C. Okay, so this is I'm looking at the space of functions from words into R in a slightly different way. Okay, and so it'll become clear why I'm doing this in a second. Okay, so the signature can be encoded as an element. So the first point here is that so with this notation, a signature can really be encoded as an element of this space. So simply by substituting these C's for these C's, the terms of the signature. So I'm going to put it in essentially like this. Or equivalently, the first term is always going to be a 1, and which kind of corresponds to the empty word. And then I'm going to look at all words of length bigger than or equal to 1, and put the terms of the signature in front of these formal vectors. Okay, and so with this definition, kind of a separate remark from the fact that I can encode the signature as an element of this vector space is that this vector space T of RD is a graded algebra. And the natural product is the concatenation product. So when I multiply two of these vectors together, EI and EJ, I kind of can concatenate stick the two vectors together. So in the kind of the most obvious multiplication that you can think of. And notice that, so this product, this is non-commutative. because as I said, these terms I just imposed, they're not commuting. So E1, E2 is not equal to E2, E1. Okay, so with this definition, Chen's identity can be rephrased in a very compact way. What it tells us is that so if I now think about the signature as the element of this big vector space, I can multiply signatures together because I can multiply elements of this vector space together. So then the signature of the full interval A to C is given by the product of the signature from A to B times the product of the signature from B to C. This is a much kind of easier formula to remember than the one that I wrote down a couple of slides ago. Okay, this is in some sense, this is the correct way to think about Chen's identity. Okay, so time for another exercise. So let's consider RD as a subspace of this vector space T of RD. So I'm just going to map an element, so a vector with coordinates x1 until xt to its kind of canonical guy, which is in front of each one of these indeterminates, and just put the coordinate of x. Then for x in RD, I'm going to define its exponential, but now this is an exponential that takes values in the space T of RD. I'm going to define it according to exactly how I define exponentiation of real numbers as a formal series, sorry, as a power series. But now the products are going to be taken inside this algebra T of RD. So it's going to be, so I'm going to define it as this power series, but this product is taken inside T of RD. So I multiply this element x, which is I treat it as I said, as an element of TRD by itself t times, and divide by n factorial. Okay. So then if I look at the natural linear path that goes from 0 to x, so the content of the exercise is to verify that that the signature of this path that goes from 0 to x is equal to this exponential of x. This exercise is more or less the same exercise that we saw earlier on when we saw that the signature generalized polynomials. So this is kind of a matter of fitting the definitions together. But now we see that there's kind of like a very elegant way, at least, to write down what the signature of a straight line is. Okay, so then basically, so what this means is that there's a very quick way now of computing the signature of a piecewise linear path. So so a consequence of this is that suppose x is a path indexed by 0 to n, where n is some positive integer, into Rd, is linear on a bunch of subintervals. So it's linear on, say, the interval 0, 1, 1, 2, 2, 3, and so on and so forth, n minus 1, n. Then we can very rapidly compute its signature over the full, at least write down a formula for the signature, which we then compute using the product rule for these formal series. So the signature over 0 n is equal to the exponential of x1 minus x0 times the exponential of x2 minus x1 times times the exponential of xn minus xn minus 1. Okay, So we see that for piecewise linear paths, there's absolutely no need to perform any integration whatsoever in order to compute the signature. And you don't want to perform any integrations. You just need to basically encode how to take products of these formal series kind of in a nice library somewhere. So in a, like maybe in a Python package or something. So then, and this is exactly what the libraries that compute signatures actually do. So they define a multiplication of two arbitrary power series together, and then they use this formula in order to compute the signature of a piecewise linear path. Okay. Okay, so yet again, another take on Chen's identity. So very briefly, I'm going to define how to concatenate two paths together. So
there's a quick question in the chat.
Yes. Oh, yeah.
In what sense is the limit of the
in what sense is the limit of the infinite sum? So yes, there is no this infinite sum is a formal sum. So it doesn't converge in kind of as an analytic object, because you don't assign numbers to these. What you should think of basically as the kth element of the sum as living in some separate kth vector space. And so think of these formal series as being like a sequence of elements in different vector spaces, like a countable number of different vector spaces. So I hope that kind of answers the question. Right, yes. Right. And maybe a point on this note. So maybe this is actually a good point to raise this. So notice that if we look at one of these infinite sums, so for example, let's take a look at this. Let's take a look at the sum here. Because x essentially belongs to Rd, which is sort of like the first level of this vector space TRD. So this is the first level of TRD. Then what this means is that x to the power of n, this is in the nth level. So it lives on it lives in a totally separate vector space from where x lives. In fact, each one of these terms lives in a different vector space. So this is kind of like the nth level. So there's no, in this sum here, there's no issue of convergence. Okay. So let's take a look now at two paths, x and y. And I'm going to define their concatenation. So I've given the formula here, but probably the simplest way to understand concatenation is to look at an example. So let's consider these paths x and y that I drew on the left. So in this picture here. So their concatenation is given by translating the path y, the base point of the path y, to the end point of the path x. So I've translated this guy down to here. So this is the translated base point of y, and then joining them up into one big path. And the way that we join them up into one big path is by essentially saying that if time runs now over the interval 0 to 1/2, so I'm going to look now only at the interval. You can do this over an arbitrary interval, but I've just restricted it to 0, 1, which is a fine thing to do because of parameterization and variance. So I'm going to chop up this interval into two halves, 0 to 1/2 and 1/2 to 1. And if my time goes along the first half, 0 to 1/2, I'm going to move along x. So this is for t 0 to 1/2, appropriately rescaled. So x to t is the correct thing to do. And then if my time is in the second chunk of the interval, then I'm going to move along y. And so this is I think this is the correct formula for that. Okay, so if you do that, then you essentially are able to glue paths together in some sense. Okay, so a couple of remarks. So if I, with this definition of concatenation, the space of paths indexed by some arbitrary interval like 0, 1, this becomes a semigroup. So I can always multiply two elements together, and this product is associative. And Chen's identity can be restated quite nicely. It tells you that the signature of a path over, so now over into 0, 1 times the signature of the path over the same interval 0, 1 is equal to their concatenation. Okay, and so I'm going to now somehow combine the shuffle and Chen's identity briefly. So to do this, I'm going to introduce one further product on the space T of RD. So for a word, I'm now going to just denote E of I, this product over these indeterminants, I1 to Ik. And then I'm going to kind of put the shuffle product, which was defined for words, onto this space of TRD. So I'm going to say that the shuffle product of two of these words, EI shuffle EJ for two words I and J, is equal to the sum over EK, where I range K over all the shuffles that appeared in I and J. So then I'm going to equip T with an inner product. So I put this bracket as inner product because now actually issues happen when about convergences. So kind of for which these all of these sort of products of indeterminants are orthonormal. So I'm going to impose that this is the inner product between I and EI and EJ is equal to 1 if and only if I is equal to J. So this is equal to 1 if I is equal to J and 0 otherwise. Is the Kronecker delta. Okay, so I'm going to impose this kind of like inner product. So notice that this is not, I've put it in quotations because it's not, now you have issues of convergence, because maybe if you take a big formal series when you, maybe because you want to extend this by linearity, maybe you get an infinity arising, but let's sort of ignore this issue for the moment. Then I'm going to define a very special subset of the space of formal series T of RD. So I'm going to look at all elements X which respect a certain identity property. So what I'm going to impose for all of these elements is that X evaluated against the word EI multiplied by X evaluated against a word EJ is equal to X evaluated against their shuffle. So EI shuffled EJ. So this was the reason for introducing this the shuffle product. This is for all words I and J. So inside of so this set G, it has a special name. These are called group-like elements, and they actually form a group. So this is quite a nice, very nice algebraic property. So okay, and so for those who are mathematically inclined, perhaps this is the kind of the nicest statement that you can find about signatures. So this kind of combines the properties of shuffles and Chen's identity. So it tells you that the function that sends a path X to its signature is a semigroup morphism from the space of paths into the group-like elements of this formal series T of RD. So this summarizes both the shuffle and Chen's identity in kind of one very kind of clean statement. Okay. So I have 7 minutes left. Let me see what, okay, so I might be able to cover the remaining kind of algebraic properties that I had in mind before maybe handing it over to questions if there are any. So one of the final properties that I wanted to cover was what happens when you reverse time. So suppose that you have a path defined on AB, and we want to reverse its time direction. So we're going to define its time reversal by according to this formula, and it is exactly what you expect it to be. So for these two paths that we were looking at before, X and Y, the time reversal is essentially just by swapping around the arrow. So you traverse in exactly the opposite directions. So the theorem here is that if you now take the product of these two signatures of X and of its time reversal, then what you get is the identity element inside of TRD. So this is the formal series. So this is really, you should really think of this as an element of TRD. And it's the one where I give our kind of the coefficient of the empty word is 1, and the coefficient of all the other words is 0. And so this is the identity under multiplication under this concatenation product that I introduced. Okay, so if you would like an explicit formula, then it's given by according to. So you can work out that this algebraic identity is actually equivalent to this one here written in coordinates. Okay, so this is what happens under time reversals. So then what happens if you combine time reversals with Chen's identity is quite a nice property. So we're going to say that a path is tree-like. This kind of links in with something that I mentioned already a couple of times, this tree-like equivalence relation. So we're going to call a path tree-like if it completely backtracks onto itself every time it moves somewhere. So this is an example of a tree-like path. So essentially what it does is it first moves up this direction, then it moves, say, along here, and then it moves back along the same exact path. And then it kind of moves outwards here, and then it might move outwards like this. And then from here it moves back along, itself, and then it kind of moves outwards here, and then maybe moves backwards all the way along, and then kind of moves back along its trajectory. So its movement is always reversed in some sense. And so this path can always be written as a concatenation of paths and their reversals in the correct order. Okay, so I haven't given a formal definition of what tree-like means, but I hope that the picture kind of illustrates what it is. Okay, so a corollary of combining Chen's identity with the time inversion property is that S of X, so the signature of a path X, is always equal to 1 if X is piecewise smooth and tree-like. So these are the kinds of paths that the signature tells you essentially nothing about. And in fact, this is an if and only if statement, even without the piecewise smooth condition, but this is quite a lot harder to prove. So you can show that if the signature of a path is the identity, then X has to be tree-like. Okay, so I think this is a probably good point to end. In the beginning of the next lecture, I'm going to look at an important compression of the signature, which is this log signature that I actually was one of the questions at the end of the first lecture. And then I'm going to so that's the final algebraic property about the signature, which again has relevance to certain applications. And then I'm going to look at kind of the other steps in the pipeline that I mentioned before. So how to go from a data to path, and then how to go from the signature to learning algorithms. Okay, thank you.
Thank you very much for a very nice second lecture. Are there further questions? you'd like to ask a question, just ask it in the chat or unmute yourself and ask it directly to Ilya.
Are there other operations that make the signature invariant? So for instance, you have mentioned that if I would just push if I have my path, I have a constant to it, just push it, the signature would be the same. Are there other operations like this that make the signature invariant?
So reparameterizing time makes it invariant. So this is one of the,
of course,
the properties. Yeah. Also adding kind of if I have a path, then in the middle of the path I kind of make an excursion out and then trace back on this exact excursion, kind of like I add a tree in the center of the path and then continue along. This doesn't change the signature. So for example, if I do something like this is my original path, and then I replace it by kind of in the middle of the path, so once I reach this point, instead of continuing, I do something like this. I go out, and then I come back along here, and then I continue along. So this does not change the signature either. So this kind of adds a tree-like path somewhere in the center. But that's essentially it in some sense. These are the only things that you can do, and without changing the signature. And this is kind of like this. That's more or less this statement over here. So everything else like rotations, compressions in some directions, those all will change the signature.
Yeah. So this is what I was going to ask next. If you multiply it, but then that sure, I understand that. Do you get properties like I multiply my path by a constant, just making it bigger? Then would I get, in terms of the signature, just the same constant multiplying the signature?
Right. Yeah, this is there is a rule for it. It's called called dilating your path. So what you basically get, so if you look at the kth level of the signature, you will that whole kth level, so all the words of length k, the signature of those words will be multiplied by that constant to the power k.
Yeah.
Yeah. So this is essentially like if you dilate it out, that's essentially what's going to, yeah, that's all that's going to happen. Yeah. Yeah. And if so, there's a kind of a more interesting or an interesting generalization to this, which is that you can hit your whole path with a linear transformation, so an arbitrary linear transformation of your vector space, and then there's a formula that tells you how the kth level transforms under this kind of hitting your path with the linear transform. You essentially this space T of RD that I described. This is a big algebra, and it's sort of like in some sense it's the largest algebra that contains RD. So you can kind of lift any transformation of RD to a transformation onto this formal space of formal series T of RD, and so then the signature basically gets hit by this lifted linear map. So in the case of a dilation, this lifting of the linear map corresponds to multiplying the kth level by lambda to the k, where lambda is your constant.
Okay.
Yeah.
Other questions? There's another question in the chat. The signature, this infinite sum, captures the features of the path completely. Are there rules that can guide us on how well a truncation of the signature will describe a path?
Right, that's a good question. There's not really any hard rules in some sense. So I can like, apart from sort of saying that if I know that the first, say, k levels of my signature are all 0, then the question is, okay, so how does my path look like? Apart from kind of like trivial statements like, okay, the levy area should be 0 and the increment is going to be 0 because those are all the terms that are encoded by the signature. It's kind of the higher order information is a little bit harder to describe geometrically. So it's a little bit I guess there's no hard rule as to which kind of tells you that, okay, bam, this property, apart from saying that the first k levels of the signature will be 0, I'm not sure that there's not really a hard kind of rule that you can put onto which tells you your path has to look like this. So,